Hey everyone, welcome back to our Digital Systems video series. In this lesson, we are going to continue our study of Boolean algebra, one of the most fundamental tools for analyzing and simplifying logical expressions in digital circuits. If you haven't watched the previous lesson where we covered the three main laws of Boolean algebra and the first 9 rules, I highly recommend watching that video first, because the 3 rules we're going to study today depend directly on what we learned earlier. In this lesson, we'll focus on the practical applications of Boolean laws and rules, learning how to transform expressions step by step and verify their equivalence using logical values. So stay with me to the end, follow each step carefully, and I promise everything will make perfect sense. Here you can see a general overview of the Boolean algebra table that we've been using. On the left column, we have the 3 main laws: commutative, associative, and distributive. In the middle column, we have the 12 Boolean rules. In the previous lesson, we discussed all 3 laws in the first 9 rules, which dealt only with expressions involving a single variable. Now, we'll focus only on the last 3 rules, rules 10, 11, and 12, which involve expressions with 2 or 3 variables. If you want, take a screenshot of this table. You'll need this table for exercises and for following this video step by step. Now, let's move on to Rule 10 of Boolean algebra. This rule introduces a very important idea: how a variable behaves when it appears both alone and multiplied by another variable. At first glance, these expressions may look a bit unintuitive, but don't worry, we're going to break it down step by step. Our goal here is to prove that the expression A plus A times B is equivalent to A. And to do that, we'll apply only the Boolean laws and rules which we studied so far. No shortcuts, no truth tables yet. Now, if we look at the expression, we can apply the reverse distributive law. That is, we can factor the variable A, giving us the term A times 1 plus B grouped inside the parentheses. You might wonder, where did this 1 come from? As we apply the Boolean laws and rules, I'll explain each step carefully so you can clearly understand what's being done here and avoid getting lost along the way. This video might become a bit longer, but don't worry, be patient, study along with me, and you'll be able to truly master this topic. Now, let me explain where this 1 comes from. Think about this. Multiplying anything by 1 always results in the same thing. So, A multiplied by 1 is still A, okay? And B multiplied by 1 is still B. This is true in regular mathematics as well. For example, 10 multiplied by 1 is still 10, okay? And for example, 100 multiplied by 1 equals 100. And x multiplied by 1 equals x itself. The same idea applies to expressions. For instance, x plus y grouped inside the parentheses times 1 equals x plus y. Okay? In Boolean algebra, this works exactly the same way. In fact, this is known as Rule 4. So, both in regular mathematics and in Boolean algebra, this rule is always valid. What this means is that in mathematics, when we see a number like 10, we are not explicitly seeing the multiplication by 1, but it's implicitly there. Okay? The same idea applies to any other number or term. Now, pay close attention to this point. In Boolean algebra, any variable that appears by itself is implicitly multiplied by 1. So when we write A, we are actually dealing with A times 1. And when we write A plus B grouped inside the parentheses, we are actually dealing with a plus b times 1, okay? That's exactly why this one appears here. Because when we apply the distributive law again to this term, we arrive at the same expression shown above. Let's verify. A multiplied by 1, it's like I said, anything multiplied by 1 is just still A. So A multiplied by 1 results in A. And A multiplied by B results A times B, okay? Well, we haven't reached the equivalence defined by Rule 10 yet. If you look at this expression, notice that inside the parentheses we have a variable added to 1. According to Rule 2, any variable added to 1 results in 1. Let's quickly verify this using logical values. For example, if b is 1, so 1 plus 1 equals 1. And if b is 0, 0 plus 1 equals 1, according to the pattern of Boolean addition. So by applying Rule 2 to this term, we reach at this new expression. So what rule can we apply here? If a variable is multiplied by 1, it simply results in itself. This is exactly what the Rule 4 states. So we can eliminate this 1 and simplify the expression, leaving just the variable a. And by applying only the laws and rules of Boolean algebra, we will reach the equivalence defined by Rule 10 algebraically. So far, we proved the Rule 10 by applying only the laws and rules of Boolean algebra. Now, let's take this one step further and assign logical values to the variables so we can confirm this equivalence numerically as well. Now, let's assign specific logical values to the variables. Let's start with a equals 0 and b equals 0. Substituting these values into the expression a plus a times b, we get 0 plus 0 times 0. And that equals 0 plus 0. And that equals 0. Okay, so the result matches the value of a. Let's test 1 to the variable a and 0 to the variable b. Substituting this value to the expression, we get 1 plus 1 times b. So 1 times b equals 1 plus 1, and that equals 1. Again, the result matches the value of a, confirming the rule. Let's move on to Rule 11. Rule 11 states that a plus a negated times b is equivalent to a plus b. Okay, first let's start by applying the Boolean laws and rules step by step. Initially, we can apply Rule 10, but only to this specific part of the expression, that is, to the variable a. It is perfectly valid to apply a law or a rule to a single term or to just a portion of a Boolean expression. So we can apply Rule 10, which we studied earlier, and which states that a plus a times b equals a. However, in this case, we are applying it in reverse form. It's important to mention that just like the distributive law, Boolean laws and rules can also be applied in reverse when necessary. Therefore, by applying Rule 10 in reverse to this term, we arrive at this new expression. Do you see how we got here? I'm going step by step so you can clearly follow what is happening and not get lost in the process. At first, this may seem a bit laborious, but there's no shortcut here. The only way to master Boolean simplification is through practice and persistence. You need to develop the ability to look at a Boolean expression and identify where laws and rules can be applied to simplify it as much as possible. That's why it's so important to always keep that table of Boolean laws and rules nearby, just like the one I showed at the beginning of the video. Now, continue the process. Looking carefully at this new expression, we can apply Rule 7 in reverse, but only to the term a. Remember that, according to Rule 7, any variable multiplied by itself always results in itself. In other words, when a variable appears alone, we can infer that it can be expressed as the product of itself. You need to develop this kind of insight when analyzing Boolean expressions. So the expression becomes a times a plus a times b plus a negated times b. Just to be clear, Rule 7 was applied only to this term, resulting in this new expression shown here. The remaining terms stay the same, okay? Now, If we try to apply the reverse distributive law to this term, okay, we would end up back at this term, okay? Which means we still wouldn't reach the desired equivalent expression. This is why I keep emphasizing the importance of having the Boolean laws and rules table with you. The process of simplification often involves trial and error. Sometimes a rule or a law doesn't work, but another will. At this point, there are no more laws or rule we can directly apply. If we apply the rule 7 again to a times a, we would simply return to the previous expression. So what can we do now? Boolean algebra allows us in some cases to add a term to an expression in order to force a useful transformation without changing its logical value. Here we can introduce rule 8, which states that a variable multiplied by its complement always results in 0. Although this technique is valid, it is not generally recommended. However, in certain situations, it becomes necessary. So adding this term, the expression becomes a times a plus a times b plus a times a negated or a bar plus a negated times b. Notice that a times a negated is highlighted because it was not originally part of the expression. We added it deliberately. Since a variable multiplied by its complement equals 0, this term contributes nothing logically. However, this 0 can be strategically useful to force a simplification. Now, we can apply the reverse distributive law to the entire expression, obtaining this new expression, okay? At this point, observe that inside the first parenthesis, we have a variable added to its complement. This allows us to apply rule 6, which states that any variable added to its complement always results in 1. Let's quickly verify this. If a equals 1, so 1 plus its complement, that is 1 plus 0, results in 1. Okay? And if a is 0, so a plus its complement, that is a plus 1, results in 1. Okay? And that's why any variable added to its complement always results in 1. Okay, so applying rule 6, we obtain 1 times a plus b. Okay, now we can simplify the 1 because multiplying any variable or expression by 1 results in the expression itself. This is rule 4. Okay, therefore we finally arrive at a plus b. So using Boolean laws and rules, we have proven this equivalence algebraically. I know this process may seem complex at first, but studying works like this. It requires effort, attention, and persistence. And with practice, this kind of reasoning, it becomes natural. Let's confirm this equivalence, assigning logical values to the variables. Case 1, a equals 0 and b equals 1. Substituting these values into the expression, we have 0 plus 0 negated times 1. This 0 negated becomes 0 plus 1 times 1. It results in 0 plus 1. And for both sides, the result is the same. Case 2. Let's test 1 to the variable a and 0 to the variable b. Substituting these values, we get 1 plus 1 negated times 0. This 1 negated becomes 0. So 0 times 0 is 0. So the result is 1 plus 0. The same on the right side. Again, both sides result in the same logical value. Confirm this equivalence for this case. And finally, let's move on to Rule 12. Rule 12 states that a plus b times a plus c equals a plus b times c. Let's begin the simplification. In this first step, we can apply the distributive law that gives us this new expression. A times A plus A times C plus A times B plus B times C. Notice that we have the term A times A, that is, a variable being multiplied by itself. In this part of the expression, we can apply Rule 7, which states that any variable multiplied by itself always results in itself. So the new expression becomes like this. At this point, we can apply the reverse distributive law to this part of the expression, giving us the term a times 1 plus c grouped inside the parentheses. The remaining term stays the same. Notice that inside the parentheses we have a variable added to 1. So we can apply the rule 2, which states that any variable added to 1 always results in 1. So the expression becomes like this. Now we can apply again the reverse distributive law to this part of the expression. So the expression becomes A times 1 plus B times C. Again, notice that inside the parentheses we have a variable added to 1. So only to this part of the expression we can apply rule 2 again. Now the expression becomes A times 1 plus B times C. And then applying rule 4, we can simplify this 1. Now the expression becomes A plus B times C. So using only Boolean laws and rules, we have proven this equivalence, confirming the rule 12. Now, before we move on, notice something interesting. There's actually a faster way to simplify this expression. Instead of factoring terms, we can directly apply rule 10. First, we can apply rule 10 to this part of the expression. That is, A plus A times C simplifies to A. The remaining terms stay the same. We can apply rule 10 again, but only to this part of the expression. Then A plus A times B simplifies to A. So we reach the equivalence defined by rule 12. This shows an important idea of Boolean algebra. There's often no more than one way to simplify an expression. Well, let's confirm this using logical values. Let's try this input combination. 0 to the variable A, 1 to the variable B, and 0 to the variable C. Substituting these values into the expression, we have 0 plus 1 times 0 plus 0. Evaluating this expression, 0 plus 1 equals 1, and 0 plus 0 equals 0. And 0 times 0 equals 0. On the left side, 0 plus 0 is 0. So, result matches for both sides. Now let's try this input combination. 1 to the variable A, 1 to the variable B, and 0 to the variable C. So 1 plus 0 equals 1, and 1 plus 1 equals 1. 1 times 1 equals 1. And on the right side, 1 plus 0 equals 0. Okay? So the result matches for both sides, confirming the rule 12. Alright, this brings us to the end of lesson 3.3. We focused on the last 3 rules, and more importantly, on how to apply Boolean laws and rules step by step to simplify expressions and prove equivalences. Notice that the goal here was not to memorize rule mechanically, but to develop the reasoning process behind Boolean simplification, understanding where a law or a rule can be applied, why it works in that specific part of the expression, and how each transformation preserves logical equivalence. This kind of reasoning is essential, because from this point on, Boolean algebra will no longer feel like a collection of isolated rules, but like a consistent and logical system that you can navigate with confidence. Thanks for watching, keep studying, and I'll see you in the next lesson.